أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم. In the last lecture we studied about information coding theory. We are going to continue uh, the source coding, what is source coding and how it is done, and what is the purpose of source coding. First of all, self-information. The amount of information revealed about an output, AJ, for example letters used in a sentence A, D, Z, etc., with probability Pj is defined as the information content of output AJ depends only on the probability of AJ and not on the value of AJ. Hence, self-information only depends on the probability of the output, but as we know that more probability means less information, therefore self-information and probability are inversely proportional to each other. The main concept over here, first of all, we have to know what is the information contained in each letter or in each symbol or code word which we are going to transmit. So first of all, we have to determine self-information, and this self-information only depends on the probability of the letter going to occur. So self-information, which is denoted over I over here, I within bracket AJ, is inversely proportional to probability of output PAJ, and IAJ is equal to log of 1 over PAJ. So we have taken log of the probability to calculate self-information, and IAJ is equal to minus log PAJ. Entropy. What is entropy? We can define the information content of the source as the weighted average of self-information of all source outputs. Suppose source outputs are S, R, B and N, and their probabilities are 0.2, 0.3, 0.4 and 0.1 respectively. Now we simply multiply the self-information of S, R, B and N with its respective probability and add the results. This gives us the information content of the information source, and this information content is called entropy, denoted by H of X. Now what we are doing is that here we know, or we have determined the self-information contained by each letter. For example, what is the self-information of A or D or Z according to their probability. For example, the probability of A is 0.1, then self-information of A is simply the log of 0.1. Now what we want to know is that what is the average information contained in that source output. Here the word weighted average actually means that we are going to multiply this self-information by its probability. So we simply multiply the self-information, that is this log of 1 over P AJ, with its respective probability and add the results. So we will multiply 0.2 by log of 1 over 0.2 plus 0.3 log of 1 over 0.3, 0.4 multiplied by plus 0.4 multiplied by log of 1 over 0.4 and plus 0.1 log of multiplied by log of 1 over 0.1. This will give us entropy. Entropy is nothing but the information content of the source output. Unit of entropy is bit, net, or ban, Hartley, or dit. So most of the time we are dealing with the digital binary system, so most probably the log of base 2 is going to be used, and this will give us this entropy in terms of bits. How many number of bits are required to uh, represent this source output. Now we have so far built the basic building blocks or concepts which are required to understand source coding. Now we are going to understand what is source coding by itself. The main objective of source coding is to reduce the number of bits in the information signal, or bits if possible. It's very simple that we want to reduce or compress the our source information which we are going to transmit. Why do we want to do so? Because we know that there is always a lot of redundant information in source which we are going to transmit, and that redundant information can be removed. This will help us in reducing the total bandwidth required to transmit the data. Suppose a DMS, discrete memory-less source, outputs a symbol from a set of symbols xi, I is equal to 1, 2, 3 to L, occurring with probabilities p of xi, I is equal to 1, 2, 3 to L. The entropy of this DMS in bits per source symbol is h of x minus summation I is equal to 1 to L probability of xi multiplied by log base 2 probability of xi. So this is the formula of entropy which we already have discussed over here. This in a statement over here, this method of multiplying the self information of with its respective probability is written in mathematical form over here, and the limit is that, or the condition is that, this entropy must be less than equal to log base 2 of L, the total length of the symbols. Log 2L gives total number of bits required when all the symbols have equal probability, and total number of bits is a power of 2. If not, then number of bits required are is equal to log base 2 L plus 1. The last equation states that if all the symbols are not equally probable, then entropy h of x must be less than the number of bits required in case of fixed length code, that is, all the symbols have equal probability. H of x is equal to log base 2L when probability of all the symbols is equal. Now first of all, let's consider an example where the probability of all the letters is equal. Let's assume 5 English letters have equal probability, that is 0.2. Then h of x, then what the probability or h of x will be? We calculate it the same method. 0.2 is multiplied by log base 2 of 0.2 plus 0.2 is multiplied by log base 2 of 0.2. Again this term is written 5 times because this 0.2 probability is same for all the 5 letters. Then the mathematical operation is done on this equation, calculation is done, and answer we get is 2.32. Now what we do is that we take log base 2 of 5. 5 is L, that is total number of letters or symbols. This also gives us 2.32. So this has been confirmed that if the probability of all the letters is equal, then it will give us the same number of bits as in case of total number of bits required to represent the total all the letters. Variable length code. When the source symbols are not equally probable, a more efficient method is to use is variable length code. Now we have to use fixed length code in case when the probability of all the letters is equal. In that case, if we are going to use variable length code, then we are not going to achieve any efficiency. But if the probability of all the letters is not the same, then we must use variable length code, and we using the information theory uh, given to us by Shannon. For example, suppose we have only the first 8 letters of English alphabet A to H. The variable length code VLC for this set of letters could be 00, 00 for A, 010 for B, 011 for C, 100 for D, 101 for E, 110 for F, 1110 for G, and 1111 for H. This is an important thing. Since the probability is not the same for all the letters, this Shannon said that you can assign fewer bits to those letters who have got high probability and more bits to those letters which have got low probability. As you can see over here, A has got higher probability, so it is less informative. Since it is less informative, we assign lesser bits to A. Here B, C, and D, and E and F are assigned 3 bits because their probability is higher than A, and they are assigned 3 bits to get to encode the information. But here G and H are assigned 4 bits because they are the least probable among all these 8 letters. Since they have the lowest probability, they are assigned the highest number of bits. This relationship is very important and very this is the heart, or this is the basis of all this information coding or this source coding. This is how we achieve the efficiency in source coding. Now comparison of FLC with and VLC means fixed length code and variable length code. Suppose we have to code a sentence, a bad cab. Now if we assume that although the probability is different for all these letters, A, B, A has got higher probability and B has got lower probability, and then B, C and D also have got lower probability. But we assume that, but we assign equal number of bits to them, that is 3 bits for each, without considering the probability of the letter. But in that case, the total number of bits are 24. But here we have used VLC, variable length code. We assign only 2 bits to A, assuming that it has got higher probability, and 3 bits to B, D, and C. When we calculate the total number of bits for this kind of variable length code, then we see that the total number of bits needed to be transmitted are 18. So we have compressed or encoded the information in lesser number of bits. Now unique code. Consider the following 2 VLC for letter A and H. This is also a variable length code and this is also a variable length code, but there is a subtle difference between these 2 variable length codes. Let's again code the same sentence, A, B, a bad cab, with both the VLCs. Using this is VLC 1. Using this VLC, we encode it and we get 18 bits over here. And using this variable length code, we encode the same word, a bad cab, and it can be represented by 9 bits. Although VLC2 gives much less number of bits compared to VLC1, but it is not unique. What do we mean by not unique? It means that when the receiver gets the stream of bits, it can interpret or decode the bits in many ways. For example, VLC2 can be decoded in the following ways. We will see those after a while. Let me just describe this thing a little bit more. What it says that although this, if you just look at the number of bits over here, this VLC2 looks very efficient coding method. But this is not the only thing which we have to consider when we are encoding our information bit. There is another important thing, is that we have to decode it as well, and the encoding method must be such that it can be easily decoded at the receiver side. So what's the problem with VLC2? We find that it is not easy for VLC2 this code to be decoded by the receiver. When VLC2 is transmitted or it is received by the decoder, this is possible that it interprets this first bit separately and it says it is 0. When it is interpreted as 0, then it will say it is A. For B, it will say okay, it is 1. And again A, it has interpreted that this 0 is separate, then it is A. So it has interpreted or decoded the received bits correctly. But this is not the only possible combination for the decoder. There is another possible combination, that is, decoder assumes that this 0 and 1 are together. Instead they are separate, they are together. If decoder makes this mistake, then it will decode this 0 1 as D instead of as A and B, and again make mistake and decode this 0 and this 0 1 separately. It combines these two zeros and decode this 0 0 as C and this 1 0 as E and C and B. So you can see that since there is no delimiter or there is no starting bit or stopping bit or synchronization bits in the encoding, so the decoder doesn't know how these ones and zeros are combined. So the coding must be such that with the encoder that there are not multiple possible combinations in the set of the code word. Each code word must be unique in the sense there is only one possible combination for that code word. So VLC2 or such a code is not uniquely decodable. Only on the other hand, if we look into VLC1, it is uniquely decodable because no previous code word is in the beginning of any subsequent code word. VLC1 code words are 0 0 0 1 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1 1 1 1 1 0 and 1 1 1 1 0. Look over here. Now look at this 0 0. There is no single 0 over here. So for decoder it's not possible that if it receives just 1 0, then it can make mistake whether it is 1 0 or 2 zeros. And similarly there are not 3 zeros as well or 4 zeros. So whenever 2 zeros are received by the decoder, it will know that it is the only interpretation or decodable code for the decoder is A. Now this 0 0 is not occurring in the beginning of any other code word. Look at here. It is not in the beginning of any code word. Here it is 1 1, it is 1 1, it is 1 1. 0 0 is unique. So whenever it receives 0 0, it will know that this can the only possible combination for this 0 0 is A. For this 0 1 0, this is again a unique one. There is no any other combination possible for this 0 1 0, and this 0 1 0 is not in the beginning of any other code word as well. But look over here for this 0 1. This 0 1 can be interpreted as separately 0 and 1, or it can be combined, this 0 and 1 to be interpreted as 0 1. This 0, it is not possible, the same thing is not possible in this VLC code. This 0 0 cannot be combined with any other code to generate any other valid code word, but these two code words are put together, then they generate another valid code word, which is D01 over here. Or if two zeros are received in sequence, then this can be misinterpreted as C. Or if two ones are received one after the other, then it can be misdecoded as 1 1 or F. So this code word is not a uniquely decodable code word, so this VLC2 is not a good code word or efficient code word. Rather, VLC1 is better. So we don't have to just reduce the number of bits, but we have to make sure also that the code words which we are going to generate are uniquely decodable.